block, Pseudoentropy and Incompressibility.
So, hello everyone. Thank you for the organizer for inviting me. So this is joint work with my student, Noah Mazor, who's sitting there.
Hi, Noah.
If anyone doesn't know him, and Jad, who is not sitting here at home. Good. So let's start with the basic. Let's start with what randomness is. Okay, we all know, but still. So randomness is a valuable resource in computer science for algorithms. Any algorithm, either we don't have them without randomness, or they're way more efficient with randomness. And definitely for cryptography. And I'm going to focus on cryptography. Okay. So the use of randomness. So not speaking general, I'm going to see something specific, but let's start. So why randomness is important for cryptography? For many reasons, but maybe the key example is one-time pad. So I want to encrypt a string. I simply XOR it with a random string, which is the key. And to decrypt, you XOR it again with the key, and you get back the string, right? So this is a great encryption scheme, secure against unbounded eavesdropping. But the problem is that the key is very long, right? It's as long as the message. And this is by Shannon back in, not in deep paper of Shannon for 48, but it's paper for 49, actually, show that this is inherent. You cannot do better than that. So what do? We use pseudorandomness. What is pseudorandomness? So actually, it's a computational analog of randomness. And actually, when I speak on randomness, I speak about uniform string, okay, uniform bits, okay? So Goldwasser and Micali gave the following definition. X over n string is pseudorandom if it's computation distinguishable from the uniform string, where computation distinguishable does mean that a polytime algorithm or polycell circuit cannot output the probability it outputs one when they get a sample from one distribution. Basically the same like probability it output one when they get a message from the other distribution. Good. So pseudorandomness is important because we can generate it. We can generate using an efficient computable function, which you call a pseudorandom generator, which is an algorithm that gets, like few truly random bits and output many pseudo-random bits. So the output over uniform short string is pseudo-random. And it outputs way more bits than the input and is efficient. Okay. So this is pseudorandom generator yield computation secure encryption, for instance, because you can now XOR the message with the output of the pseudorandom generator. And now you use the key, which is key, K can be much shorter. Good. And constructing PRGs from basic assumptions is challenging. It's not the topic of this talk. I'm going to relate to it slightly. It's not the topic of the talk, but this is like, just keep in mind. Okay, so we start with the randomness. And let's go zoom out. Let's speak about entropy. So entropy, this formulation is measure the randomness of a string. If a string is truly, or random variable is truly uniform, then the entropy should be maximized. If it's constant, the entropy should be 0. And the entropy function gives you everything in between. An example, if it's an n-bit string, the entropy is n. If it's somewhat randomness, then the entropy is something between 0 and n. Okay, good. So entropy, it seems like rather arbitrary formulation, actually, under some assumption. Assumption is the only formulation, but to see that, for instance, this is the minimal description length for x. If you want to compress x, you can compress it to the entropy. I'm going to address it in a few slides. But it's also the number of random bits, uniform random bit required to sample x. And as computer scientists, it's also what the number of random bits can be extracted from x. Okay, so entropy really captures something really basic, fundamental about distribution. There's other version of entropy, most notably mean entropy, which is the worst case version. Mean entropy for random variable, it's the log 1 over the probability of the most likely event. Good. So like we have for randomness, we have pseudo-randomness. For entropy, we have pseudo-entropy. Actually, for entropy, we have many analogs. Okay, this is a big part of this talk, but let's start with the first one, which is pseudoentropy by Russell, Hastad, Levin, and Luby back in 1989. Says the following: a random variable has pseudoentropy at least k if there exists a different random variable y, which is true Shannon entropy. The formula I gave before is what's called the Shannon entropy. Is true Shannon entropy is at least k, and is computation distinguishable from x. Okay. Why is it important? There's many variants, pseudo-entropy, metric pseudo-entropy. But why is it important? Why pseudo-entropy is important? Or why computational analogs of entropy are important? The reason is that we understand information theoretically very well. Maybe not us specifically, but people understand information theory very well. Way better than we understand computation, right? So computational analog of entropy allows us to do the following. We take a result that someone proved rather easily on the information theoretic regime, and then use exactly the same tool on different random variable, and claim for the security by the fact that if it works from the real entropy measure, it should work also when the computation analog. Otherwise, you can break the analog. Okay. Otherwise, you can break. You prove that something that you thought has a lot of pseudoentropy doesn't have a lot of pseudoentropy. Okay. This is a great paradigm, very useful paradigm, all over cryptography. I guess also over complexity as well. So that's an example. I want to go from pseudoentropy to pseudorandomness. So I have a source that has a lot of pseudoentropy. I want to get pseudorandom generator, say. So we know that if a random variable has a lot of entropy, actually I'm slightly cheating, it should have a lot of mean entropy, and you apply a randomness extractor, I'm cheating again, you need to see it, but let's ignore that, that's for the sake of the presentation. Then you can extract something which is basically what I said, the number of random bits it has, the entropy. So if it has entropy k, you can extract k random bits. So now, okay. So now, if you have a different random variable whose pseudo entropy is k, okay? His entropy might be very low, but his pseudo entropy is k. And then you can apply the same extractor, as long as it is efficient extractor, and you argue that his output is computation distinguishable from uniform. Why is that? Because if you could distinguish, you could break the pseudo entropy of the original random variable. This may be the most basic example how to exploit computational analogs of entropy. Very simple. Okay. Let's see another analog of entropy, which is next block pseudoentropy, slightly more complicated. It says the following. This is joint work with Omer and Vadhan and Salil also from 13 years ago already. So a random variable, we can think about it as block as bits, with n bits, as next block pseudoentropy k, at least k actually, if there exists a different random variable, y, which is again y1 to yn, such as the following rules. First, given any prefix of x, you cannot distinguish between the next bit of x from the ith bit of y. Okay, they are jointly distributed. Y is jointly distributed with x, otherwise it doesn't make sense. Again, you cannot distinguish, given any prefix, you cannot tell whether the next bit you're getting from x or from y. And if you sum up the entropy of y given the prefixes, then the sum of the entropy is k. Okay? The easiest way to figure out what it means, that it's general, okay, so xi is somewhat hard to predict given the prefix y, it is hard to predict as yi is hard to predict. So it measures the unpredictability of the source, okay? And those, I guess, those of you familiar with Yao and predictability, predictability says that no efficient algorithm can predict the next bit, given the history, better than guessing. This is a quantitative variant of it. Say, well, maybe you can, but not too good.
You should think of H as mean entropy, right?
No.
Because for guessing.
Bits. Yeah, if you think as bits, you can think about it.
I see.
So, so say, well, you can predict. Maybe some of the bits are very easy to predict, but overall, you cannot predict too well. What is not too well? Not too well than k. Okay. And it's used to construct, actually the best construction, I would like to say the best construction of one function, of Pseudorandom generator for one function, but a recent result of Noam and Raphael improve it by log n bits. So now it's not the best construction, it's still the best construction, I guess. Okay, and it's defined for arbitrary block length, but I want to focus on 1-bit block length. Okay, so we've seen two computational analog of entropies. There are way more. So this is the general paradigm. Okay, identify user property of distribution of high entropy, next bit unpredictability, uncompressibility, whatever, and then define computational analog only of this property. Okay, and then use tool that works for this property and apply them on the analogs. Okay, so here's an example. Pseudorandomness, pseudoentropy, unpredictability, next bit pseudoentropy. I'm going to introduce more. Next slide. Actually, there are more. Before that, all this notion capture what's called indistinguishability of distributions. There are other notions like inaccessible entropy. It captures like something very different that high entropy sources have. We use, say, to construct statistical ID commitment.
Just a curious high-level question. So in the information theoretic setting, everything is very robust in the sense that all these notions are equivalent. And
Exactly.
In the usual computational setting, they're all kind of separate.
Exactly.
And now what happens in between? Say if we have very weak computational models, if you look at the AC0 parities.
So for your first part of the answer, a good answer. For a question, a good answer. For the second one, I don't know what happened. Look, the other computational models.
For the second question, those who are interested, you know who to work with.
So, but here's a good question. Why do we need many analogs? I mean, for entropy, we have only one notion of entropy. It gives them all. Why do we need many analogs? So I thought of the following example. It's a bit stupid. Okay. So you have an elephant. An elephant is both huge and gray. Okay. Giraffe is also huge, but is not gray. Okay. But sometimes, if you only want to exploit the hugeness of an elephant, then it's also applied to giraffe. But if you want to exploit the fact that an elephant is gray, then it doesn't apply to that.
Now I'm convinced.
So the idea is you apply entropy. High entropy distribution have many properties. You know, like you take one of the properties and you find the analog from that, and then whatever only all the tools that only require this property works for your analog. Other tools are not going to work because giraffe is not gray. Okay. Good. So this is why we need many analogs. Okay, different analogs are used to do different things. Okay? So here's another analog, which is the topic of this talk, which is compression. So what is compression? A compression scheme is a pair of algorithm, encoding and decoding algorithm, such that if you encode and then decode, you get the same value. Okay. Right? And the goal is to compress. The goal is that you find the encoding such that if you sample from the distribution, you get the average shortest length. Okay? Compression. Each of us who took like basic information theoretic course know what compression. And Shannon showed, this is a beautiful result, that compression is really the size of the compression is captured by the entropy up to 1 bit. Okay, you can compress a random variable exactly to its entropy up to 1 bit. At least if I restrict myself to what prefix encoding, which means one encoding is not a prefix on a different encoding, which is important. Otherwise, when you actually use it in practice, when you send many symbols, you cannot decode. Okay, so if you think about prefix code, which is for this talk only concentrated for prefix code, the compression rate is exactly the entropy. Okay, up to 1 bit. So Yao, back in 82, in a paper, which I think the same paper with one permutation and whatever. It was one section. One section.
In that paper, he gives the equivalence of computational indistinguishability and
predictability. And the thing is,
he does the XOR lemma. He does pretty much everything. most of the paper, he's talking about the effective entropy.
Yeah, so this is one result
All
of
the
this
other
paper.
stuff
By the way,
Very secure computation.
there's other results that no one cares about. So, right, there's one or two sections no one cares about till now. Probably in 50, 100 years, people will start caring about the other two sections, the missing two sections. So if you want to find a result that will be important in 50 years. Good. So it's called effective entropy. So the following, well, I don't care what I call effective. I don't care that you can compress a distribution to very few bits. The question, can you do it efficiently? Okay, so said the effective entropy of X is the minimal encoding length, but you restrict yourself to polynomial time encoding and decoding algorithm. Note, by the way, that even if the distribution is computable, for every X you can say is probability, compressing might be difficult if the domain is large, because Huffman encoding, for instance, is polynomial in the size of the domain. So if the domain is exponential, even though you can compute the probability, it might be difficult to compress. Huffman encoding is the one encoding that achieves that. Okay, prefix encoding that achieves that, but it's inefficient in general. Good. So what is incompressibility? It's the opposite. X is k-incompressible if no efficient algorithm can compress it to less than k bits. Very natural definition, okay? And it's interesting if the entropy is smaller if we have a gap. Computational analog of entropy are only interesting if the entropy in the analog is larger than the real entropy. If it's the same like the real entropy of nothing, I mean, you're not going to get anything. So it's interesting if the k is like 100 bits incompressible, but its real entropy is 5, okay, or even 99. And this notion is not well understood. So, you know, like why it's not well understood. For instance, we don't know even what simple manipulation do to this notion. If you take parallel instances, like in only any other notion of analog of entropy, when you take parallel repetition, well, it behaves like it should do, like it just multiplies. Here we don't know that, okay? We also don't know the relation to other computation notion of entropy. So typically we have good understanding like whether one analog implies the other or not. Okay, here we didn't. One exception, Barak, Shaltiel, and Wigderson back in 2003 showed the following. You can extract k minus omega of log n bits of pseudo-random bits, but distribution not with k-incompressibility, stronger variants of compressibility, actually worst case variants you can think about as mean entropy. Okay, very beautiful result, very beautiful, elegant proof. The construction is very simple. You just apply reconstructive extractor on the source. You apply the reconstructive source. If someone distinguishes it from uniform, then because the extractor is reconstructive, you can get back the source. So you compress. Okay, those of you know what reconstructive extractor, if not, forget about it. So it was used actually, it took 70 years for this result to be used, and it was using the construction of PRG from hardness in a recent result. So this is great, but I'm claiming that it's not really the right result, okay, in several senses. First, you know, like complexity type of constructions, okay? From hardness, for worst case hardness assumption, you get a PRG, a Pseudorandom generator. No, like Nielsen-Wigderson, yeah, different type of thing, Nielsen-Wigderson constructions. So why it's not the right result? I mean, it's a great result. Why it's not really the right result? First, it applies to different notions of incompressibility. Second, you lose omega of log n. You know, cryptographer, we don't care about log n, but not about omega of log n. But thirdly, it doesn't say much about, the source itself. You say you have a source, it's incompressible, you do something to it, then you have something pseudorandom, but it doesn't say enough about what, if you have incompressible, what does it mean about you? Can you relate it directly to something? You can only apply something, then say something about it. So it's very nice, but it's still, there's a missing of understanding, yeah.
It's obvious that in information theoretic regime, incompressibility gives you extraction. I mean, it seems like it's connected to Shannon entropy, not to.
There's no incompressibility. I mean, in the if you do
information theoretic,
you're right, because of mean entropy. Great, because that's why their notion is mean entropy, basically. Their notion also, actually, it's a great comment. Their notion also applies to mean. Nerzo implies in the information what regime mean entropy. I saw something.
So it's not the incompressibility. So, but can you hope to extract from incompressibility? You don't, right?
No, you cannot extract because it's not a worst case scenario. You cannot do that.
So, okay, so you cannot hope to.
You cannot hope to do that in the standard. Still, it's somewhat similar notion. Maybe you can hope that when you do repetition, then you can extract. But the problem is that when you do repetition, we don't know that it works actually. Again.
Like encoding and decoding needs to be efficient.
Then we do. It's exactly that's the entropy. It's just the entropy.
That's exact same.
Exactly the entropy. The sum is same as right? I said elephant has all these properties. We care about different features. Okay, so this is the world as far as we understood it before this result. So we have this maybe the basic, basic notion of computational analog of entropy. There's pseudo-entropy, next bit pseudo-entropy, and incompressibility. What is the relation? So first, these two are equivalent to one function. What do I mean by that? I mean that if you have non-trivial pseudo-entropy, the pseudo-entropy is noticeably larger than the real entropy, then it implies one function, and one function also suffices by constructing Pseudorandom generator to construct that. Same for next block pseudo-entropy, but not for incompressibility. We didn't know that. And pseudo-entropy implies next block pseudo-entropy. This is easy to show. This is actually by definition. And it implies incompressibility also because if you can compress, basically the proof that how to distinguish with high entropy distribution. This is easy to show that it's not the right way to go. You cannot do that. However, the source with next entropy is very large, but its pseudo entropy is very small. By the way, how I'm doing with time with all these stupid jokes? I think I waste all my time.
More than 15 minutes
left.
Maybe 20 minutes.
Okay, sorry. Okay, no more jokes. So there's okay. Start just to write it down. Yeah. Anyway, never mind. So I skip it. So it's easy to see that next block pseudo-entropy does not imply pseudo-entropy. It's a huge gap. Also, it doesn't imply incompressibility. Let me write this example. You have a pseudorandom generator G. Think about G of X and X. The pseudo-entropy is nothing, it's like X because you see X, okay? Also, it's very easy to compress it because you compress X. But the next bit pseudo-entropy, if you look at it from left to right, there's a lot of next bit pseudo-entropy coming from X. Okay. There's local separation between, actually Hotek, I think, did it, local separation between compressibility and pseudo-entropy, that it doesn't, there's a source that has a lot, is incompressible, but it doesn't have a pseudo-entropy, but again, only via oracle separation. But this was the missing link. I mean, we didn't know whether something which is incompressible has a lot of next bit pseudo-entropy. Basically, okay, so that's one question for getting the result. About this error, I mean, this seems, when you think about the first time, say clearly incompressibility implies one function, but if there's no one function, you can compress. So it's not actually so. So that's one note where we only care about samplable distribution, so which can sample they're using a efficient algorithm. So if one function do not exist, then you know that you can randomly, thanks to Russell, you can randomly invert any function. Okay. Then you say, well, here's the way to compress. You get a distribution, a sample distribution, you invert it, and then you output the pre-image, right? But who says that the pre-image is shorter than the output? Maybe to sample a distribution, you need a very long pre-image. So you can try to do pre-sampling, etc., but you don't get the right what you like. Okay, it's not clear. Maybe you can do it directly, but it's not naive. Yeah.
You can do it.
Using pre-sampling, subsampling.
No, like hashing.
Hashing, yeah. Well, that's a subsampling. Yeah. I guess, but you don't get exactly what you like.
Well, it's not prefix free.
It's not prefix. Okay. Good. And I guess that it's not prefix free, and I guess you're going to have error.
What?
You're going to have errors as well. Because dashing, if you're not going to have error.
Well, you can just, If you
That's,
have errors, you can just give the whole string.
no, sir. So if you do hashing, so it's not clear how do you decode, because to decode you need the perimeter of the hashing, but if you try to invert it, you might be have error. Let's take it offline, but
Okay.
it's not clear that it's working. I mean, it seems plausible, but it's not trivial. That's what I have to say. I mean, the fact that Russell solved it 40 years ago doesn't mean that it's trivial. It's complicated, but this is not the main. I say it's not trivial. Good. So first, what is the relation between incompressibility to other computational analogs of entropy? I don't know. And in particular, does non-trivial incompressibility imply cryptography? You can add the asterisks to that. Maybe Russell knew it 40 years ago, but again, here's a very simple proof, which is tight with the non-errors. Okay, so here's our result. Our result is the following: impossibility actually implies next bit pseudoentropy. And exact characterization, if X has k-incompressible, then it has next bit pseudoentropy k-2. We're losing 2 bits. Okay. 1 bit is unavoidable because it might be that even that a source is a k in the information theoretic settings. It might be the 1 bit gap. Okay. Okay. You can compress to sometimes to you have to compress. You have to spend 1 bit more. Okay. This is Shannon. Second bit, we don't know. We spent time. We didn't manage to get rid of the second bit. Few corollaries. So if X is sampleable with non-trivial incompressibility, then namely it's greater by 2 bits plus its entropy, then it implies one function. And second thing means if there exists no one function, and if every sampleable X can be efficiently compressed to its entropy plus 2 bits. Again, no error or nothing. Okay. So what is the proof idea? The proof idea is if a source, counter positive, if X doesn't have a lot of pseudoentropy, we want to compress. So if you have a source X, you have a source X.
You look over there.
Yeah, right on the
You have a source where only is k-2 bits are unpredictable if you go from left to right, but all of these are predictable. It's very easy to predict them. Okay, they're all zeros. So definitely you can compress. Okay, because simply output the last k2 bits. Okay? So if it doesn't have a lot of next bit entropy because of trivial reasons, then definitely you can compress. It becomes harder if some bits are hard to predict, some are not hard to predict, but you don't know where. It becomes much harder if this bit is somewhat hard to predict. It's this bit somewhat hard to predict. Everything sum up to k, or even all bits are slightly hard to predict. How can you compress? Okay. So basically, this is our answer. And yeah, let's go to the result. So actually, the result, the proof simply does, you have to write down the preliminaries and you have nothing to do else. I mean, so nothing else to do. It's technically, it's the simplest paper we've ever wrote. I mean, it took us a time. We invented some of the tools that people knew 40 years ago. Actually, one of the tools 10 years ago, like arithmetic encoding. But after you try to come up, you find out that someone already did it better than you, and thus you plug everything together and you get a result. Okay, so really, it's one of these cases that you're lucky. Everything is ready. You just need to plug them up. Okay, so what do you know? So every 15 minutes more, we said. If I recall correctly, no. Okay. Okay, 15. Yes. Okay, so let's be slightly about compression scheme, slightly more details. That's definition. I'm going to speak about K divergence. Then I'm going to speak about compressing Ron distribution, measure using K divergence. And then I'm going to cite a beautiful result by Salil and Colling from 10 years ago that show that actually next block pseudoentropy is equivalent to what we call KL hardness. We'll speak about arithmetic encoding, and when I'm going to finish writing them all, the proofs will go pop up. Okay. Good. So we focus on non-uniform case. For now, distinguish our polysize circuits. simplifies our life. Okay. So again, we know what the compression scheme for a distribution. Prefix key, it means that the encoding of one element is not a prefix for encoding a different element. And we have also what's called C-point-wise scheme, which means that the encryption size of every element is at most a log over 1 over the probability plus C. Okay, this is like point-wise promise guarantee about the encryption, the encoding length. And it's immediate that if you have a C point-wise scheme, then the compressing is just the entropy plus C. It's most entropy plus C. This is and by the way, Huffman code, for those familiar with for Huffman code is 1 point-wise. You only spend at most 1 bit more than 1 over log over 1 over the probability. It's prefix free, which is great, but it's inefficient. Again, running time depends on the support side. And we want to speak about arithmetic encoding, which is only 2-wise, point-wise. This is why you pay the 2, but in our setting is efficient, even though the support is exponential in our setting. I don't know, actually. No, you know? Anyone? They have point-wise promise. I'm not sure. I don't know.
They're competitive with the finite automata.
Yeah,
They don't have a
Efficient,
distribution, right?
but
They don't have a distribution, right? It's a.
do we achieve the entropy? I don't know. I mean,
They don't look on a distribution, right? They look on one sample.
Yes.
so k-divergence. So k-divergence, remember what entropy is. K-divergence is slightly more complicated knowledge of information, which is actually sort of a measure of a distance between distributions. It's defined like that. It is you take the expectation with respect to the left-hand side over log the ratio of the probabilities. That's a formula. I mean, don't stare into it too much. But the way you should express it, and I'm going to justify it next slide, is the surprise when you expect to get a sample from Y, but you're actually going to get a sample from X, the amount of surprise, okay? And yeah, never mind. So here's a nice fact. Let encoding, some encoding scheme, which is C point-wise for Y, okay? So again, you develop an encoding scheme for Y, which is great, it's C point-wise. But then you use it with X. How good is the encoding? Okay, you develop it for X, Y, but you use it for X. So very nice result information. Here we say, well, you achieve that, which this is what happens if we develop encoding scheme for X, plus the penalty, which is the relative entropy between X and Y. Okay, this is the only property we need for k-divergence for this talk. Okay? We wrong and you encode wrong distribution, you pay this back. Okay. Good. Okay, skip this. That's what we said before. What is next to Pseudoentropy? Now the result by Salir and Collin say the following. First, we have the notion of estimator. So an estimator, just a string, it gives algorithm that gets a string, it output a probability between 0 and 1. No? Very simple. But given this algorithm, you can define a very long distribution. So first you feed him the empty string, it gives you the distribution of the first bit. Then you take the first bit that's been sampled, you feed again, you get the distribution for the second bit. You sample a color of this distribution second bit, you feed it again. Now with 2 bits, it gives you distribution for the third bit, and so on. You can continue what you like and define, for estimate and define the distribution. Okay. And X, distribution X is k-hardness K, if no polysize, for every polysize estimator, the k-divergence between X and YE, this distribution is at least K. Again, so your goal in life now is define an estimator such that mimic X. Okay, it's similar to X, and you have to do it using estimator. And k-hardness means that you cannot do that. For any efficient estimator, the k-divergence between X and this distribution is at least K.
So E of y1 through yi minus 1 is a number between 0 and 1?
No, E is a number, but every time you take a sample. Every time you take a sample. So it gives you a number, you take a sample, this is the first bit.
And then you update your number.
No,
Next bit.
this is a bit, you take the first bit, it's a bit, you give the first bit to E, it gives you a second number between 0 and 1, you sample the second bit. Now you have 2 bits. You feed them E, you get a number between 0 and 1, you sample accordingly, you get a third bit.
Okay. And now we're thinking of E as like a polynomial time algorithm?
Yeah. So you can, if E is efficient, definitely you can sample it Y.
So what does the superscript P stand for? I don't understand. What is when you say Y1 sub P?
Is a little
It should be E, a change from P to E, and I forgot. So this is it. Okay, thanks.
These are the real, the ones inside of the real coins, or the?
This is the coin sample according to E. So again, this is a random process. I take Y, the way I sample Y1 P, I feed E with empty string, it gives me 0.4, I sample a bit with probability 0.4 is 0, probability L1 is 1, give again to E.
But why
So
do you call
it's a
it
distribution over distributions, right? It's a distribution over distributions. What
Yeah, but it's you can think, that's thinking about it as random
but
variable.
it-
This is really random variable. It's the way
It
to
has nothing to do with the actual
E?
output. Why do you call it an online?
because the way you use it, the estimator only give you 0 between 0 and 1. So the way you generate is in online. You generate the first bit, you feed him, you generate a second bit, you feed him, and then but the way it's adapted, maybe adapted.
To X.
It's not related to X at all. But the goal, your goal in life is to find the best E such that this is small. Okay? You know what X, there's distribution X, maybe it's hard to sample, whatever. Your goal in life is to find E such that if you do this process, the k-divergence between X and YE is small. Seems like a very strange game, right?
So when you compute the KL divergence of X, you're like doing this bit by bit.
I can do it by using chaining, yeah. I can do that using chaining, right?
Yeah.
So yeah, but you don't like use the Y's, you use the X.
Use it, yeah. So beautiful result by Vadhan and Zeng from 11 years ago says the following. Actually, hardness K minus entropy of X is equivalent next bit pseudoentropy K. It's equivalent, okay? Okay, it's not, so this seems very strange notion, but this notion equivalent. A random variable have K minus its entropy, KL hardness, if and only if is next bit pseudoentropy is K.
Can you give us some intuition why this?
So for example, if it's pseudo-random, then the one side is, so should this be the result?
If it's pseudo, yeah, if it's pseudo-random, it's going to be our result, but let's think about it.
Like
So, if it's pseudo-random, it's not clear, because if it's pseudo-random, the k-divergence, what do you do with k-divergence? I mean, k-divergence is going to be huge, even though this looks pseudo-random.
right.
Right?
So it's going to be, yeah, so it's going to be, I
This is
see.
a real k-divergence, nothing to do with the pseudo-random. So beautiful result, use variant of the fact that Boltzmann distribution have maximum entropy with respect to linear constraint. I taught this result twice. I still don't really understand it. I mean, you can follow the line. There's some magic happening there. Really recommend to see the proof. Okay. In effect, here, why do I do that? Because I'm going to use it to show that incompressibility implies next bit pseudo. So actually, I'm going to use this notion. I'm going to use that if a random variable has a next bit pseudoentropy K. So I want to show that if a random variable is incompressible, okay, then I can find out an estimator. So sorry, I got confused. I want to show that if a random variable doesn't have a lot of next bit pseudoentropy, then I'm going to use this result to show that YE has a small k divergence, and then I'm going to use it to compress X. Okay, so to use one slide, yeah.
So I mean, I wouldn't know how to put it, but should we really be that surprised? Because this k-hardness definition really talks about like trying to predict the next thing, which is also what the next bit pseudoentropy is. The next bit pseudoentropy tells you, like, if I knew all the previous bits, how hard it would be to sort of how much entropy or how hard it would be to predict the next one. Whereas this is also sort of the game that you play in k-hardness. So, like, I don't know, should we really be like?
Yes, because how do you move from prediction to no? So no, if you don't have next bit pseudoentropy, it means for every y you can predict. How do you? There's many different y's, for instance. How do you use that to come up with one distribution that achieves small k level? This is one strategy. Okay, I said for any adversary, there's many.
I didn't say that I could prove it.
Yeah, no, it's highly likely. The rough intuition very maybe doing right.
So it's in the interest of Yuval's health.
Yeah, good. So let me just so here's the trick. So I say that if there's next bit estimation, then you can compress. Namely, if this does not hold, okay, it doesn't have a lot of next bit pseudoentropy. Therefore, by Salil and Colin, it doesn't have a lot of hardness, then you can compress. Okay, this is what we want to do because we want to show, well, incompressibility implies next block pseudoentropy. So we do the counter positive. It doesn't have a lot of next bit pseudoentropy. It doesn't have a lot of hardness. I can compress. This is going to be contradiction. So given the estimator, again, it doesn't have a lot of hardness. It has an estimator. I'm going to compress X using compression scheme for YE. What's great about YE, because it's a pointwise, I can really compress it, okay? Using what? Using something called arithmetic encoding. So I can really compress it. Okay, YE I can compress it. It's one of these distributions because it's generated online manner or adaptive manner, whatever you want to call it. I can really compress it to not with entropy, with entropy plus 2. Okay? But how much I'm going to pay for using for S a compressing scheme for YE? How much? Exactly compressing Ron distribution. So I'm going to pay this quantity. I'm going to pay this quantity. But if this quantity is small, I'm not going to pay much. And this is all proof. Okay? Again, if a source doesn't alert, if I want to prove that incompressibility implies next bit pseudoentropy. I say, well, it doesn't. Next bit pseudoentropy is small. Therefore, by Salil, is k-hardness is small. Okay. What does it mean? There's this one E such that this value is small, this quantity is small. I'm taking this E, I'm building a compressing scheme for the distribution YE. This is easy because E is efficient and YE is built in an online fashion. And now we're going to apply this compressor for X, not for YE. I'm going to pay. How much are going to pay? This quantity. But this quantity is small. That's all. This is the proof. Yeah.
I just realized if I asked a question, I wouldn't be able to talk.
Okay. So okay, so basically, so this is the proof, okay? Assume X has no k-2 next entropy by Vadhan and Zhang. There's an estimator with scale divergence between X and YE is small. Lemma, which is there exists 2-point-wise compression for YE, which is just it's already people know to do it. This is what's called arithmetic encoding. And by compressing Ron distribution, the encoding length of n is just h of x plus 2 plus the scale divergence, which is. I said we did nothing. We just plug 3 results together and we got the result. This arithmetic encoding, I spent a lot of time in the flight doing these pictures, but you know, too bad for you. Okay. When you want to do uniform compressing, it's slightly more challenging, but skip it. So, okay, so that's let me end. So, open question. First, can you get rid of the 2 bits gap? Reduce it to 1 bit? Don't know. And second question, there's totally no implication of these results. Okay, we thought we were going to have, but till now we found no. But you know, for Wigderson and Shaltiel and Barak, it took them 17 years to find application. So you know, take your time. You have 16 more years to do that, and thank you.
Russell sets up. We can take a question even by Russell. Multitasking.
If you didn't care about two, but just wanted to log on, could you just do the IL?
What can I do? I mean, so one second.
I just compressed by inverting it. And then,
If you want to do one,
randomizing it, you just do like if you didn't log in bits instead of two, and then you can like log in bits is 500.
no, I mean, I will compress. You don't know, but there's no one function. What to do? There's no one. You cannot invert. You just want to go from incompressibility to the next.
Okay, but if I just want to do that, it applies one functions, then
Apply one function.
Yeah, you can.
just do it and then
Then compress.
prefix string
I
code.
guess it's going to be error, but
Yeah.
let's see. Maybe.
So
Distribution.
multiple copies of the same text.
We don't know how to compress it. No.
Yes. One lesson for Russell's talk even before the talk is that if you ask for a 30-minute talk, you get 30 minutes, even if you Russell. So,